on Tuesday, at the very end, I had missed the factor of 2, so let me start over there. So if you remember, we were doing the projectile problem. Right? Why? Don't make it. So here you have a y-axis. Wait, do it quicker. Make a straight line. So this is the y-axis, which is your x-axis. And you launch something, let's say at some velocity v0. I'm just writing the magnitude. I'm not writing it as a vector. This is where the action is happening, not next to you. I'm talking to you, you don't have to turn back. And this is theta. I'm calling theta 0, so I think I wrote theta 0 in my notes. But if you follow the trajectory, as we discussed, it's a parabola. Nothing changes there. But there are certain things about the parabola that are easy to find. One, for example, the height h, which is the highest point this projectile will reach. We know already that the acceleration due to gravity is downward. So we can easily find, for example, what h must be, because what we would do is we would split up this velocity along the x-axis and along the y-axis, just like we have been doing for a while now. So this would be v0 cosine of theta, and this would be v0 sine of theta. Because it's going up, the vertical velocity, it should be positive in sign. So therefore, we can look at the kinematic formulae, and we can try to figure out how to figure out this maximum height. The first thing that we notice as far as maximum height is concerned is that this is when the vertical velocity must be 0, right? Because the vertical velocity slows down until it reaches 0, at which point the direction of the velocity flips and it comes down. So at the highest point, we find on y, we call it the vertical velocity at the top. That must be 0. The initial vertical velocity, let's say v0y, is v0 sine of theta. The height, it rises, so that will be y. We can call it h. It can be positive because it's going up. And the acceleration is minus g, or minus 9.8 meters per second squared. Okay? So we can easily find h. What formula would you use? You don't have time. How many formulas have y in them? 2. One of them contains time, one of them does not. So it must be the other one, because this one, I don't have any time information. So you need to be intuitive about how you use the formula. So v final y squared is v0y squared minus 2 g times h. So therefore, I forgot this factor of 2 when I wrote down h. We know that v final y is 0, as I told you, it stops in top before it flips. So therefore, clearly, h must be v0y squared divided by 2g. And therefore, this would be v0 sine theta squared, or v0 squared sine squared theta 0 divided by 2g. Just a reminder, why do you have a thing open in front of you? At the back. I don't allow laptops or cell phones or anything like that in my class. You should know better. So basically what it is that you should know that sine of theta whole squared is usually written as sine squared of theta. So that's a notation that if you are not totally familiar with, you should. Okay? Any questions? Okay. So this is the 2 that I missed. If you go back and look at the lecture notes from Tuesday, towards the very end, I forgot to put the 2 in because I was trying to rush. So couple of things here. One thing that we discussed is that if theta is 90 degrees, if you recall the table that we had, sine of 0 is 0, but sine of 90 is 1. So therefore, the maximum value that h can have will come when theta is 90 degrees. Indeed, if you throw it vertically up at velocity v0, it will reach the highest point with velocity v0. But if you throw it at an angle, it will reach a lower point. So that's the intuitive interpretation of what we are talking about. So therefore, h would be v0 squared over 2g, which is something that actually you've seen before, if theta were 90 degrees. And that would be the highest possible value that you can attain in this problem. Okay? Any questions? All right. Good. So now we can actually do a few more things. One of the things that we can easily calculate is what is called the range. What is the range? Range by definition, range has a definition, a technical word. That is, this distance here is actually called range. It can be denoted by r or d or whatever. Yeah.
I have a question. So
yeah.
if 90 degrees is like for highest, then like, how about longest?
We'll come to that. So that will depend on the range,
So
right?
if you use 0, then it doesn't work, right?
Right. You have to call for something like that. It's one of all.
I mean, I suck at gold.
Practice it. You'll enjoy doing it. All right, but I'll tell you in a moment. So that's the range. The range is the actual horizontal distance that it covers. So you can clearly see that actually to calculate range, so to find range, we can set what to 0. It's something we can set to 0 if you want to calculate range. What would that be? There is no horizontal acceleration. If I set angle to 0, then I want to calculate range, right? Huh? Yes. Huh?
Acceleration.
I have no control over acceleration. I have gravity and I have no acceleration on horizontal. To calculate range, there is something that I can set. I told you range is the whole thing. Look at the picture. Huh? Y equal to what?
0.
Y equal to 0 because the displacement should be 0. So to calculate range, y is equal to 0 because the net displacement, right? In spite of the fact that it travels the whole thing like that, the net displacement is 0. That's why. Because it goes and comes back to the very same point, ultimately, right? So the net displacement is 0. These things are very important. So therefore, I can, since now to calculate range, I actually need to know the time of flight. There is no other way I can do it. My plan would be something trivial. I would think about range as v0 cosine of theta, which would be horizontal velocity, times the actual total time of flight, t. So that would be my strategy for calculating range. Because that's the easiest way in which I can get range. There are many ways I can get range, but this would be a very easy way of getting range. So if I know the total flight time, I can, because there is no acceleration along the horizontal direction, v0 cosine of theta times time should give me the total distance of travel, in this case the range. Therefore, let's find the time. I can again, since I want to use the fact that y is equal to 0 and I want to use time, I have no choice but to write y equals v0, in this case v0 sine theta times time minus 1/2 g t squared. And y of course is 0, so I would just set this equal to 0. Any questions so far? Yes.
Why do you bring along the negative 1/2 gt squared?
Why not?
What line do you?
G is negative. We are assuming to be a negative quantity. But V0 is not a negative. So once I put the V equal to plus, it's only natural that I make sure that I account for the negative G. Right? That would be good. I mean, that's the thing that you can do it any way you want. I can leave an A there and then put a minus G later. But I just skipped an object there. All right. Yeah.
Why in that equation is it sine instead of
Right now, I'm just considering the vertical motion, right? So vertical motion will tell me, I don't know much about the horizontal motion other than V0 cos theta, right? So to find the range, my argument was that I need to get this guy. I don't know what this guy is. So I can get the total time of flight by setting y equal to 0 and just doing the vertical motion. That will give me the total time of flight. This is by the way the same problem I gave in the last quiz. Then I calculate the total time of flight, just set the displacement to be 0. Then one answer would be t equal to 0. That means it doesn't leave you. And the other answer would be that the total time of flight will fall off. So that's exactly what I'm doing. So therefore this is 0, so I can write V0 sine of theta times time is equal to 1/2 GT squared. I can write, at this point, I would like you to do things the following way. You should say that since t is not equal to 0, because t equal to 0 is a solution to this, as you can clearly see. Right? So if you put 0 here and 0 squared here, this would be clearly satisfied. But that's not something interesting, because that means it's not even flying. So I can easily then write V0 sine of theta is 1/2 GT. If I cancel out the t's, from that I can find t is 2V0 sine of theta over g. So that you see, in terms of known quantities, is my actual total flight time. Any question? Yeah?
We are saying the ball was thrown at a 90-degree curve.
No, I'm not saying that. I'm saying I'm just considering the vertical piece of the motion. The ball was thrown at theta. Yeah, the vertical motion is V0 sine theta. That's all it is done. So as far as the vertical motion is concerned, yes, it's going vertically up. But the ball wasn't thrown vertically up. That's a resolved problem from the original. Uh-oh, somebody is very late. What happened to you, buddy? You know, after 10 minutes, you get a 0 in the quiz, right? You were in my class, right? Are you in my class? Yeah, come down here. Yeah.
So that V0 sine theta, that's the velocity of inverted motion.
Yeah, starting goal. Any other question? All right. So if I know t, then I'm in business, right? Because my goal was to find the range. So range is V0 cosine of theta times time, and time is 2V0 sine of theta over g. Can you simplify it? Can you simplify it? Do you know any state that can help us? No? So I can certainly combine the V0s, right? So I can write V0 squared over G. And then I'll be left with 2 sine theta cosine theta. Can 2 sine theta cosine theta be written differently? What is the usual way of writing 2 sine theta cosine theta? High school. Think high school. Sine 2 theta, that's right. So you guys are in pretty bad shape, right? So sine squared theta plus cos squared theta is what? And why is that? Yeah, but what?
Oh, I forgot that this is one.
You forgot the reason why?
Yeah.
That's criminal. How can you forget the reason why? That's Pythagoras' theorem.
Oh, so, yeah.
Okay, that's all right. So that's one, right? There are several of these that you should know. Sine 2 theta is 2 sine theta cos theta. These are things you should know. Cos 2 theta is 2 cos squared theta minus 1 equal to 1 minus 2 sine squared theta. So these are some very, very standard identities that you actually should know. Uh-oh, somebody just came in. It's always interesting when you point out somebody just came in, the person who came in looks in every possible direction. All right, so there we go. Okay. So these are things that you got to know. By the way, there is another thing that I forgot to mention when I was introducing how to calculate the angles in trig. We talked about the fact that theta, sine theta, cosine theta. Remember I made a table like this some time back? So this is 0, sine 0 is 0, cosine theta is 1, theta is 30, means sine 30 is half. This is root 3 over 2. I told you guys you can write it like this because 1 and root 1 are the same. 45 would be root 2 over 2 for both. This is coming down, that's going up. 60 degrees is root 3 over 2. And then this is going to be 1/2. And 90 would be, sine 90 is 1, and this would be 0. Remember I discussed this some time back? And I asked you to memorize. So if you haven't memorized this thing, then you should, because it'll come quite handy going forward. Of course, if you get very badly stuck, I will help you, but this is something that you should know. But one of the things that you also should know is that I only told you from 0 to 90, and that means I only gave you how to calculate the sine and the cosine, and hence the tan, because the tan is sine over cosine. Right? So you can calculate the tan once you know sine and cosine. So at any rate, I showed you how to get these from 0 to 90, but you can get it for beyond 0 to 90. So let me work that out for you. By the way, let me just finish this and then I'll tell you. So R, therefore, is V0 squared over G, and this, therefore, is sine of 2 theta. So to get the maximum possible R, to get the maximum possible range, suppose you're playing golf, throwing a ball, what should your angle theta be? 45 degrees, right? Because if theta is 45 degrees, then sine of 2 theta would be 90, sine 90 is 1. So therefore the maximum range you can have, R max, would be V0 squared over G, and this would be at theta equal to 45. Okay? Question? You guys everything? Follow the problem? Let me now briefly show you how to calculate sine and cosine when the angle exceeds 90 degrees. So there are two identities here that are very important that one learns in elementary trig. So one is that if I have two angles, let's say angle A and angle B, and I want to add the two angles, so I will calculate sine of A plus B. So this can be 30, this can be 90, the sum can be 120, for example. Then this identity goes like this: sine A, cosine B. If this is plus, you have a plus cosine of A, sine of B. Okay? This is a very important identity. And this identity you should know. I told you I'll tell you what to know as we go along. So this is why I'm telling you all this. You should know this. If I have a minus here, instead of a plus, I put a minus here instead of a plus. Okay? Plus minus. Likewise, if you have cosine of A plus B, this formula is slightly different. Cosine of A plus B. So this is sine A, cosine B, cosine sine. This is cosine A, cosine B. But if this is plus, we'll get a minus sine A, sine B. So once again, if you want to find cosine of a large angle, and if you know cosine of smaller angles, then you can actually construct. If it were a minus here, then this would become a plus, and that is written like this, flipped. So in other words, if it's cosine A minus B, cos A cos B plus sin B. If cosine A plus B, it's cos A cos B minus sin B. In this case, these two signs are the same. In this case, these two signs are flipped. That's what the notation means. Question? So this is how you calculate large obtuse angles. There are more, but right now let me not go overboard. As long as you know these things as we get through exam 1, I'm pretty okay with it. So let's get back to the projectile problem, just to analyze it a bit. So we realize that R is V0 squared over G sine of 2 theta, right? We realize that. So now we can actually see something interesting. So if theta, if I make a table of theta and R, it's pretty clear that if theta is 0, nothing happens. Then the range of this would be 0, because there is no horizontal motion if theta is, there is no motion, no vertical motion if theta is 0, nothing is happening, so R is 0. If theta is 15 degrees, then sine of 2 theta would be sine of 30. Sine of 30 would be a half. So it will be half V0 squared over G. So therefore, this would be, if I write it in decimal, 0.5 V0 squared over G. Okay? So now suppose I go to sine of 30 degrees here. Then 30 times 2 is 60. Sine 60 is root 3 over 2. So if I actually make it 30, then this would be root 3 over 2. What is root 3? 1.732. Don't forget it, please. What is half of 1.732? 0.866. Right? That shouldn't be 85. 0.866 V0 squared over G. You see now it's increasing ever so slightly. If I hit 45, then of course I get the maximum range. So that will be V0 squared over G. Right? So that will be just V0 squared over G. As you can see here, as I raise the angle, the range goes up. But the range cannot go up beyond a point. The range goes up to maximum possible range because sine cannot be more than 1. So if I now go further, let's use this board here, I'll raise this. If I go further, if I go to 60 degrees here, then this becomes 120 degrees. I can calculate 120 degrees by basically doing 60 plus 60 here. And the answer I'm going to get is going to be root 3 over 2 V0 squared over G. And therefore, this will be 0.866 V0 squared over G again. So in other words, beyond 45, my range actually begins to shrink from the maximum range that I attained. At 75 here, it will be 150 degrees. I can calculate that as well. It will come up to 1/2, same thing. Etc. Okay? So you see, when you shoot projectiles, the picture goes something like this. If it's a 45-degree launch, you obviously get the maximum possible range. There's no question. That's your R. But if you do at, if you shoot it at 30 degrees, let's say, you get a smaller range. If you shoot it at, let's say, 60 degrees, it will actually reach the same point. In fact, it turns out that if this is 30 and this is 60, total is 90, they would get to the same point, complementary angles. So you can get the same range by hitting at 30 degrees or at 60 degrees. And the whole, assuming that there is no air resistance. So the whole thing depends upon how much time you want to put this ball. Oh my goodness, somebody in the back is playing with the phone. You are dead today. You're not going to get it quick, so I'm sorry. Green jacket. You are done. All right, so 60 and 30 is 90. And what you have is essentially the same range. So let us say that I shoot a projectile like this at some angle. Okay, high angle. Then what the math is telling us is that it is always possible to shoot a projectile at the appropriate lower angle such that they would have the exact same range. Okay? That's what the math is telling us. So in general, if a projectile is shot at a certain angle, and the angle is high enough, then you can always shoot a projectile at a somewhat lower angle and intercept the projectile that was sent first. So let's see if we can do a problem like that, because those problems are actually quite interesting, not quite easy. So let's say there are two cannons that are fired. Okay, so this is my x and my y-axis. And let's say I fire one cannon, the first one, at higher angles, like this, calling it 1. And I fire a second cannon a little later at a lower angle. So now it's not only lower angle, but it's also a little later, because that's the thing that happens when something is at a high angle. So this is quite interesting then. You can actually intercept a missile, let's say, within a certain time window. Because all you have to do is to shoot the second missile to intercept the first missile by shooting at a lower angle, if that is possible at all. So this is the reason why, for example, if you have a missile coming your way, you have a super tiny window of time within which you must react. So if the distances are large, that time window is larger. If the distances are small, that time window is vanishingly small. So this would be my number 2 projectile. So let's say I have two angles. The angle here, number 1, is 60, and the angle here is 45. Okay, in degrees. This missile is shot at time t1, but this missile flies for time t1. And the second missile flies for time t2. Naturally, the second missile has been fired later. Suppose I know that v0, which is the velocity at which it is being launched, v0 in both cases is 250 meters per second, let's say. So, for the missiles to be able to meet, what are the conditions that must be satisfied? What are the two things that I must keep in mind? Times are not the same. But what are the two parameters that must work properly for the two missiles to meet? Yes?
The same place that they meet.
Same place. And this is the motion in 2 dimensions. So how many parameters would you get? 2 parameters. An x final and a y final. Right? If you want to say that the two must meet at some point in space, then you need 2 coordinates, right? X final. So we call this point here, the height of this point y final, and the x coordinate of this point, x final. So I have x final and y final associated with this point right here. So I can ask the question, for example, given what I already know, that 60 and 45 degrees are the angles, and both missiles are being shot at 250 meters per second, I can ask the question that what must be the time difference that I have to react? So in other words, what must T1 minus T2 be? That's not a super easy question, but it can be calculated. So let's see if we can do it. A relatively simple calculation. So, since we know that we have two conditions that we must satisfy, let's first do the simple thing. The simple thing would be that I should be able to write an equation connecting the x there. Since the x motion is not accelerated, I should be able to write x final equal to horizontal motion would be v0 cosine. In one case it will be, let's say, 60 degrees times t1, which is the time taken by the first slide, which is the higher angle. And this would then be 250 meters per second times cos 60. Cos 60 is root 3, cos 60 is half. Cos 60, yeah, let's leave it as cos 60 for now, times T1. And this quantity is also the same as V0 cos 45 times T2. That's for the second missile. So that will be 250 meters per second times cos 45. And this will now be T2. So since xf is the same in both cases, I should now be able to write 250 meters per second cos 60 times T1 is equal to 250 meters per second times cos 45 times T2. And since 250 and 250 are the same in both cases, that cancels out. Cos 60 is a half, and this is root 2 over 2. So that means I should be able to write T1 is root 2 T2. So in other words, I can already relate the two times, although I'm not in a position to calculate what T1 minus T2 is. I can relate the two times, just from the xf being the same condition. Are you guys with me, or have you lost me terribly? I actually haven't done anything weird, I promise. All I have done is I have simply written down the x and y pieces of the motion. In fact, I haven't even written down the y piece. I've just written down the x piece of the motion of the two missiles. That's it. That's all I have. You can't blame me for doing something that's weird or difficult or that. This is not difficult. All right. So let's see if we can now do the vertical piece, because vertical piece should give us something neat as well. The vertical piece tells us that y final is the same in both cases, which means I should be able to write 250 meters per second. This is the V0, T1, sorry, V0 sine of 60. Don't talk, please. Times T1 minus 1/2 G T1 squared. Is that okay? Acceptable? Similarly, I should be able to write 250 meters per second for the second guy times sine of 45, right? Times T2 minus 1/2 G T2 squared. Remembering the T1 and T2 are related by T1 equal to root 2 T2. So in other words, T2 is small. If you multiply T2 by 1.414, almost 1.5 times, that will be your T1. So I need to equate these two things. And at this point, I'm going to do that, I'm going to actually save me some writing because I can. So do I need to? All right, let's just write the way we want it. So I should be able to write 250 meters per second times t1 times root 3 over 2 times t1. So root 3 over 2 times 560 minus 1/2 g t1 squared equals 250 meters per second. Sine 45 I know is root 2 over 2 times t2, but t2 is t1 over root 2 minus 1/2 g t2 squared, which would be t1 over root 2 squared. So that will be basically 1/4 t1 squared. How many are lost? Yes. Where are you lost?
I think I just get confused with like the trigonometry aspect of it.
So far I haven't done any bad trick because I've just been taking cosines and sines and I'm doing something very simple actually. Let me just use some color to identify. What I'm doing, the point here is that I'm simply equating the two vertical motions by saying that y-f is the same in both. All right? So this is the equation for the first projectile, which is time t1, and the angle is 60. And this is for the second projectile, time t2, angle is 45. Right? So both are traveling yf for them to meet. Same thing I've done there. So it may look messy, but it's not messy. Once you start to write and understand where things came from, things snap right on in place. Okay? Any other? Yes?
Can you just go over and on the second half of the last one?
Yes. What this by the way comes from here, right? So I have this is the equation for T1 unchanged. That's the equation for T2, but then T2 from here is T1 over root 2, right? So I'm just writing T2, T1 over root 2, and then T1 over root 2 whole square. Okay? Yes?
So for x, d dt.
Yes, exactly.
The other equation.
Yeah. Yeah. Okay. I know it's a little bit nerve-wracking, but let your nerves not get unnecessarily wrapped. So at any rate, we now have a quadratic equation that we need to solve. If I simplify this, which is at this point quite doable, the following will happen. So let me just skip some steps here and write. Please skip the one step because it's aggravating viewers at the moment. It'll do you some good. So 250 meters per second. And here you have root 2 minus 1 over 2. So this term comes from combining that term and that term. And then T1. And so I admit I'm skipping some steps. I'm pulling this to the other side. This is 1/4. This is a half. This is a 1/4. G times T1 squared. So since T1 is not equal to 0, I can actually cancel out one of those T1s. And I can simplify my life considerably in doing so. So I don't really have to solve the full quadratic equation because I have managed to simplify this, fortunately. It's not always guaranteed, but in this case it works out nice. T1 should be T2, why? I'm just doing
on the equation, T1 over root 2 should be T1. It should be T2.
T2 is T1 over root 2. I've eliminated T2.
Oh, okay.
Right? I've got rid of it. Any others? Yes.
Why is
I just basically pulled the root 3 over 2 times 250 T1 and the 250 times root 2 over 2 T1 over root 2 on the other side, combine the two terms. I didn't show you how I did it. So that's it. I just skipped a step. Alright, so at this point you can calculate T1, right? So T1 luckily is 2 times 250 meters per second. I don't have to carry 250 meters per second. I can just carry V0. There is no harm done. This would be roughly 10, because that's G here. And then I have root 3 minus 1. Root 3 minus 1 is 0.732. So if you work it out, this thing comes approximately to T1 comes approximately to 37.3 seconds if you do the math. Of course, I have approximated and rounded off. So I'm not going to do the math completely. And now, since I've already found T1, I can actually find T2. And T2 would be T1 over square root of 2. So T2 now would be, if you do the calculation, it's approximately 26.4 seconds, which means that T1 minus T2 would be 37.3 minus 26.4 seconds. So that would be not very much, actually. 26 and roughly of the order of approximately 11 seconds. Now, less than 11 seconds, 10.7 seconds. So it basically is telling you that you have a less than 11 second window to shoot the second missile to actually intercept and destroy the first missile. It's a very simple calculation at some level, but it's very eye-opening because as long as the angle is high enough and you can shoot something at a lower angle, you'll be able to intercept the first one. Questions? Yes? If you shoot at a lower angle to begin with, and you can't go much lower, then you are in trouble. Because you have, well, you can probably vary the velocity and still make it, but it's going to be a little bit more complicated. Yes? I absorbed the two terms. So basically, this minus half became a plus half. And here you have a square root of 2 squares, that's a 2 and a 2 4. So half minus 1/4 is 1/4, and that's where that 1/4 comes from. Okay? Yes?
If you were doing this on a test and we didn't have a calculator, would we be allowed to sort of simplify the root 3 as just like 1.7? Because it's easier to take like 500 times 0.7 than 0.732.
Yeah. I'm not really interested to remember the whole number perfectly well, as long as you get the whole part. Things make sense at third point. Okay. Good. There is a problem I assigned from outside the textbook. In fact, all problems I assigned in this set are from outside the textbook. Let me just briefly point out how to do that problem. I will probably not go in the level of detail that I would like to go to, but it's in my notes, and you can take a look at it online. So let's say that this is a hot air balloon. And hot air balloons usually have somebody in them if they're going to be interesting. And that's somebody somebody hot air balloon. Hot air balloon is coming down, let's say. Coming down at a velocity v. Let's call it v0y for now, with minus 20 meters per second. You guys know. And what you do is, as the balloon is coming down, you throw a rock horizontally. So if you throw a rock horizontally, like I use the velocity calculate, let's say the velocity is v0 and this is 15.0 meters. Okay? V0x is 15. So you know that the acceleration due to gravity is already downward. So that is g is downward. And let's say when this whole thing, the releasing of this atom, it's at some height from the ground. And naturally, since you have thrown it like this, it's going to come down like that and hit the ground. So this is how the rock will come down. So let's first go through the exercise of figuring out what would be the initial velocity of the rock. So if you want to find, for example, what is y at launch? What is the height of the balloon at launch? If we want that information, then we need to take into account a few things. So first, to find y at launch, we actually, you're also told, let's say, that from the time that you release this to the time it hits the ground, that t is 4.00 seconds. You're told that. You ignore the time taken for sound to reach your ear and all that. Assume that that is easy. You just came in, right? Why are you coming now? I won't be giving you a quiz today. So, so that's how it's going. You're welcome to stay for a few minutes. I won't be giving you a quiz. All right. So essentially now I can actually calculate this y by writing y equals minus 20.0 meters per second times t. T is known. Minus 1/2. 9.80, let's say, meters per second squared times t squared. So t is 4. And so I can actually calculate this y. And if I do this calculation, you will find that the answer I would get is basically minus 160 meters. So minus 160 meters comes from the following. It comes from the fact that when I'm releasing, wherever I'm releasing this, I'm setting locally y equals to 0. So therefore, this height will come out to minus 160 meters. Which means, as far as height from ground is concerned, the height of the balloon would be 168 meters. 160 meters. Actually, the exact calculation is 168, but we round it off at 168 meters. Okay, so that's pretty easy to do. Let's now see what is the horizontal distance traveled by this rock. The horizontal distance traveled by the rock is quite easy because you already know the horizontal velocity. So let's call that distance x. So this is the horizontal distance traveled by the rock. And that would be x equals 15.0 meters per second. That's the speed times time, which is time is 4.00 seconds. So 15 times 4 is 60, so that's 60.0 meters. Okay. So you now know the height from which the rock was released because you knew the time. I gave it to you. And you also know how far out the rock. These are the questions that are asked in their homework problem. So you know this side and you know that side, so now you can calculate the distance. This distance, that is between where the rock was released and its final point. Okay, that's one of the things that you are supposed to be calculating in the problem that I assigned. So this is how you do the problem there. The main point here to note is that if you are releasing something from a balloon, let's say, if you throw something, and let's say the balloon is going down, as in this case, or going up, with some velocity v0y over there. And this velocity here is v0x. Then the initial velocity of the rock would have two pieces. One would be the upward velocity of the balloon itself, because the rock was in the balloon as it was released. And the other is the horizontal velocity with which you released it. So what would its trajectory be? If I ask you to draw this trajectory as I release this and the balloon is going up, how would it be? It will go up. You'll be amazed at how easy it is to get fooled to thinking that the trajectory would be like this. No, it won't be like that. The trajectory would be, this will be going up and then coming down, because initially you had the balloon going up. So for gravity to take over, it will take a little bit of time, and for that reason, it's going to go up and then come down. Okay? Questions? That makes sense? So we can now do something a little different. Thus far, we have been doing kinematics, let's transition beyond kinematics. So now we'll completely switch gears. So back in the day, basically in the late 1500s, one of the most creative scientists and artists combined, and everything else, engineer combined, was a guy called Galilei. So Galileo was a remarkable fellow. And if you read about Galileo, if you haven't read about Galileo, then I would suggest that you just take a minute or two on Wikipedia, for example, to look up some of the things that he managed to do in one lifetime, which most people probably can't do in many lifetimes. So one of the things that Galileo figured out was what we now know as Newton's first law. Actually, Newton's first law originated with Galileo. And the way Newton phrased his first law was almost identical to the way Galileo phrased it, and then went on to build further, which, as far as I know, Galileo did not do. Newton arrived quite a bit after Galileo. In fact, Newton was born the year after Galileo passed away. So their lives didn't overlap. So we call them Newton's laws, which is what your chapter 4, I think, in the book is. Most books dealing with mechanics is chapter 4. But the thing actually started with Galileo. So let me just read it out for you. I'll write it later, but let me read it out. So listen very carefully to the wording, because this wording was Galileo's wording, translated into English, obviously. It was in Latin originally. So Galileo Galilei said, a body at rest remains at rest, and a body in motion continues to move, but at a constant velocity, along the straight line, that is, unless acted upon by some external force, or an external force was his wording, translated correctly. So the point was, a body at rest remains at rest, and a body in motion continues to move at a constant velocity along a straight line unless acted upon by an external force. So let's see what it really means. What it means is, at the tongue-in-cheek level, if I'm at rest, nobody pushes me, I should be. That apparently seems pretty simple. But am I at rest? It depends upon how you look. If you're looking at it from the moon, if you could, would it seem like I'm at rest? No, because I'm on the surface of the Earth, and the Earth is rotating. So I certainly am not at rest. In fact, the Earth rotates reasonably quickly for hours, the kind of speed that we can handle. So I'm not at rest if looked at from the moon. I am not seen to be at rest if you are actually walking past me. In fact, with respect to you, I would seem to be moving in the opposite direction. So it depends upon who is measuring. The concept of rest becomes a very dicey concept. What is rest? Is there anything at rest in the universe? And the answer is no. As far as we know, there is nothing that can be claimed to be absolutely at rest anywhere in the universe, as far as we know. So how do we know that Galileo Galilei got it right? The answer is we don't really know, beyond a point. We cannot precisely experimentally check it to say that Galileo was right. Something at rest continues to be at rest unless acted upon by an external force. Now, see how layered the concept was, because if I am at rest, I don't do anything, I should continue to be at rest, right? So that's pretty trivial to visualize. But Galileo was not just thinking about me standing in the room. Galileo was thinking about anything at rest anywhere in the universe in a much larger context. And so for him to pull out what would be the concept of rest, when nothing around him is really at rest, is pretty darn remarkable back in late 1500s. So this is what Galileo then said. So by default, Galileo pointed out what is force. Because if you are acted on by a force, you shouldn't be at rest or moving at a constant velocity. What does it mean? So even constant velocity is excluded. If you are moving at constant velocity, let's say you're driving around at 50 miles an hour, there is no net force acting on you. That's what Galileo then pointed out. He also implicitly then said that if you are not moving at fixed velocity, if you are not at rest either, then there must be a force, external force acting on you. That's what he said. And that is what Newton went on to make into a precise mathematical statement by saying that the force that acts on you is equal to the mass of the body on which it acts times the acceleration of the body that is being acted upon, body of mass m. So F is equal to ma. That's where it comes from. Now, what is amazing is as follows. Our human brains can pretty reasonably visualize, if you train yourself, how F equal to ma works, although it is extremely tricky. So it's a multi-layered concept. And that's the reason why this course is difficult, basically, because at some sense you are trying to figure out in detail how Newton's laws work. And that's what we do in all the chapters, starting with chapter 4 onward. Now, a couple of things that let me make a point here. Remember I said that no external force acts on you if you're moving at fixed velocity. That's what Galileo said, and that's what Newton reiterated, and that's what we call Newton's first law. Now, if you're going around in a circle at fixed speed, is there an external force acting on you? Why? So your velocity is continuously changing. You see, even going around in a circle at fixed speed, your velocity is continuously changing. And therefore, there is a force acting on you, as per Newton and Galileo. There is another very interesting and very rich concept that was pointed out, and that is Newton's laws are only going to precisely work when the measurement is being made using a reference frame, so using axes, x, y, z axes, whatever, which has to move at fixed velocity, and that fixed velocity can be zero locally. So I can measure. You are sitting there. I can measure your position. If you're walking around, I can measure your thing. But I am at rest locally. You're not looking at it from the moon or anything. Locally, this is a rest frame, and I can measure, for example, her speed or velocity or whatever. That's fine. That works. But if I am actually walking faster and faster, if I'm accelerating, then Galileo said that Newton's laws won't quite come out as per expectations based upon things would change. In other words, if I'm in an accelerating frame of reference, then I make a measurement. That measurement will actually not give me unique results. But as long as I'm making a measurement from a frame of reference, which is either fixed at rest or moving at fixed velocity, then Newton's laws will work. Any frame which is at fixed velocity can be zero, is called an inertial frame. And any frame which is accelerating is a non-inertial frame. So even sitting on Earth, we are going around in a circle. And because we are going around in a circle on Earth, we actually are accelerating. So sitting on Earth, we don't have a really precise inertial reference frame. In other words, sitting on Earth, we are always bound by some level of precision as to how accurately we can check Newton's laws. Checking Newton's laws precisely is extremely difficult. The other point that I want to make is that because Earth goes around and that we are accelerating, it turns out we don't feel very much because we are made that way. We evolved over more than 2 billion years. So what happened was that we can feel the force of gravity, which is about 9.8 meters per second squared. But the force that comes around from the Earth's rotation, that is many, many times. In fact, I can give you the number. That's something I'll show you next week. If you do the calculation, that is about 0.034 meters per second squared, as opposed to g being minus 10 meters per second squared. So it's very, very tiny, so we don't feel it. So we sort of are in an inertial frame approximately, but we are not quite. So I'll get into these with more precision next week, okay? So next week, of course, we have the test, but Tuesday we are doing this. All right, let's get started with a quiz. Move your stuff away.